at our transformations lesson 8. So this continues from lesson 7 yesterday, and really what we're looking at is if we started off with the function y equals f of x, and then we became the function y equals a times f of b times x minus h plus k, what did all these a's and b's and h's and k's do to the graph? So a belongs over on the other side of the equation. It was my stretch factor. And when it was over on this side, it was the 1 over a. So then the stretch factor becomes a. So that's why it's written this way. You have to think of what would it have been like when it was on the other side. My replacement would have been y with a 1 over a times y. With my b, my replacement, I'm replacing x with a b times x. So I get a 1 over b stretch factor. They're written as absolute values because the stretch factor is always given as a positive value. If that number is negative, we split it and we have a stretch and we have a reflection. So that's this next part, if a is negative and if b is negative. Then we have the translation. That's replacing x with an x minus h. So when h is greater than 0, I go to the right. And when h is less than 0, I'm replacing x with an x minus negative h. And that's where I get the x plus h, and I go to the left. The same thing happens when I'm adding my k value. So when I replace y with a y minus k, I'm going up because my k value is greater than 0. And when I replace it with a negative value, so minus negative k, which is a plus, then I'm going down. So again, if you go back to the replacements, the pattern is the same for the replacements. It's only moving those y values to this side of the equation to write it as a y equals that it starts to look opposite. Because this plus k would tell me that I would be going up, but that plus k was a replacement of a minus k when I started off with. Okay? And then we talked about yesterday the order, using the sort, so you can stretch or reflect because they're multiplying ideas. I'm multiplying by a factor. I'm replacing y. When it's negative, it's replacing y with like a negative y or a negative 1 times y. So it's still a multiplying factor. So we multiply before we add and subtract. This is the adding and subtracting. Okay? So if we look at the first class example, the graph of y equals f of x is shown here. It says, consider the function defined by the following equations. 2 times f of 1/2 times x plus 5 minus 8. So if the equation is written in this form of y equals a times f of b times x minus h plus k, what are the values of a, b, h, and k? So what is a? 2. What's b? 1/2. What's h? Negative 5. Good. And what's k? Negative 8. Okay? So if a is equal to 2, what is that telling me to do to the graph? My a value is my vertical stretch. So a vertical stretch. What's my factor? So think, what was that? What was the replacement to get that 2? Y with a 1/2 y, because it would have been a 1/2 on the other side. So this is a vertical stretch by a factor of 2. Okay? And then my b value is horizontal. So what's my replacement? If b is equal to 1/2, what did I replace x with? I replaced x with a 1/2 x. order to get that into the equation, so that my stretch factor is a factor of 2 again. What does my -5 tell me to do? And that's because it was a replacement of x to x plus 5. And what does my -8 tell me to do? The k value.
Vertical translation.
8 down. Okay. And that again is because I would be replacing y with a y plus 8. So now when I go to sketch this graph, the order that I sketch the graph in is very important. I have to start off with my stretches first. So I pick points to stretch, and I'm stretching them both vertically and horizontally. So I'm stretching the x and the y value. So I'm going to first of all reposition my graph because I know it's not right. So when I'm looking at this graph, if you look at the vertex, which is at 0 and 0, if I stretch that 0 and 0, is it going to move? No, because I'm multiplying them both. It's 0. When I multiply it by anything, it's going to stay where it is. Okay, so now I have 1. And what are the coordinates here? What's the coordinates of this point?
1 and
1 and 1. So if I stretch the vertical by a factor of 2, it will become
2.
2. And if I stretch horizontally by a factor of 2, it will become 2. So this point of 1 and 1 is going to become 2 and 2. My -1 and +1 would become -2 and +2. And then I have another point which is at 2 and 4. So if I stretch that by factors of 2, where would my 2 and 4 go? Four and 8. So 4 and 8. And where would -2 and 4 go? -4 and 8. So this becomes the graph of my stretched function. The graph of my final function means that I have to take, after the stretch, I have to translate it 5 to the left and 8 down. So I take these 5 points that I've drawn and shift them all to the left 5 units and down 8 units. So there's 5, 2, 4, 6, 8, 5. And there's my final function. This is my y equals 1/2 square bracket, or sorry, 1/2 f of 1/2 x plus 5 minus 8 is the one that I have in red. And if you were able to, this graph in blue should be the exact same as the graph in red if I drew it like with a high degree of accuracy. Because it's the same graph, it's just been translated at that point. Okay? So if we look on the next page, do you guys recognize what this function is? the x squared function. So if this was x squared, what would be the equation for this function? Well, I go back to those replacements. I replaced y with a 1/2 y, x with a 1/2 x, x with an x plus 5, and y with a y plus 8. Those were my replacements that we discussed on the previous page. I can do them in groups of x's and y's. I don't want to do the x's together, but I could do these two at the same time. So instead of y equals x squared, I would have 1/2 y equals 1/2, oops, 1/2 x all squared. So what is 1/2 x all squared? 1/4 x squared. And I want to write this as a y equals before I do the adding of the translations. So how do I move this 1/2? Multiply by 2. So I multiply by 2 and I get y. When I take 1/4 and I multiply it by 2, I get 1/2. Okay? So now I get this part. If I replace y with y plus 8, and then x with x plus 5, there's where I'm at. Now what do I do? Minus the 8. So I get y equals 1/2 x plus 5 squared minus 8. And if I was to put that into my graphing calculator, I should get the same graph that I drew in red on the previous page. Okay? So let's look at the next example. The graph of y equals f of x is shown. You're not going to be able to put this into your graphing calculator. It's a piecewise function. You're not going to get that shape onto your calculator, which means you're not going to be able to put the transformed shape into your calculator. You have to go with the characteristics. So if you notice, I very seldomly have I actually pulled the calculator out to show you what it looks like. So if I'm asked to sketch the graph of y equals -2, f of x minus 3 plus 1. It's okay, I swear.
I can't do it.
What are my replacements?
Is y replaced with a -1/2 y?
Are you asking or telling?
I'm pretty sure I'm telling you.
You're telling me? That's a good thing that you're telling me, because you're telling me correctly.
Okay. Isn't y also replaced with a y minus 1?
Yes? Which one's done first, though?
So 1/2.
Right. Okay. And what else am I replacing?
X with an x minus 3.
Okay. So this replacing y with a -1/2 y, what is that going to do to the graph?
Vertically stretch it by a factor of 2.
Okay, vertical stretch, factor 2. Is that the only thing it's going to do?
And reflected.
And where is it going to reflect it?
And the x-axis.
Okay. Because this -1/2 gets split into the 1/2 y and the -y. And then my x minus 3 and my y minus 1, what will that do to my graph?
Move it up 1 unit and to the right 3.
Okay, so 3 right, 1 up. So we always try to do our left-right translations before our up-down, just because x comes before y. So what I would recommend doing is I would do this in 2 steps. I would do my stretch and reflect in 1 and draw what the graph looks then, and then I would slide that graph instead of trying to hold it all in your head for the whole part. So pick a point. where's it going to go?
-3, -4.
Okay, and then when I flip it,
-3, +4.
right. Okay, so do that to the next 4 points. Okay, so if I look at these, the second point, with this second point, the y-coordinate is equal to 0, which means when I do those vertical stretches, it stays at 0. And so does the other point on the x-axis. Then I have this point that is a y-coordinate of 4. When I stretch it by 2, it goes to 8. When I reflect it, it becomes -8. And then my +5 goes up to 10, and then comes down to would be -10, which is off the grid. So if I joined those points together, that's the graph that I get. And now I would take that entire graph, so I would take those 5 points again and move each of those points 3 units to the right and 1 unit up. So 3 and 1, 3 and 1, 3 and 1, 3 and 1, and then this one, when I go 3 and 1, would bring me to here, here. 5, 6, 7, 8, 9, 10. Oh, 1 up, so I need to be right here. I can't see anymore. So 3 to the right, and 1 up. There we go. And there's my new graph. So that graph in red should be virtually a copy of the one that I had in blue. It's just been moved over the 3 and the 2. Or sorry, the 3 and the 1. Get the right color. There we go. Okay? So if we look at question number 3, we have a function called f of x, and we're going to write the equation of the function after we put in the following transformations. So I have a horizontal stretch by a factor of 4 about the y-axis and a vertical translation of 5 units down. What are my replacements?
Y with a 4y. X with a 4x.
There we go, x with a 4x. And what else?
Y with a y plus 5.
So my equation of y equals f of x becomes y plus 5 equals f of 4x. How come I could do that all in one step?
Because the transformations you were given are perpendicular to each other, so it doesn't make a difference.
Yeah, they're opposite to each other. I've got a replacement on x and a replacement of y. So I can separate those two. Okay? Okay, so try B.
Don't you have to move the 5 over in A though?
Oh, sorry. Y equals f of 4x, like that?
Yeah.
Yeah. So we have a vertical stretch by a factor of 3/5 about the x-axis, a reflection in the y-axis, and a horizontal translation of 2 units left. What are my various replacements?
Y with a 5/3 y.
Okay,
X with a negative x.
x with a negative x.
X with an x plus 2.
into my equation, 5/3 y equals, and I can go f of negative x. I can combine those two. And then I would move my 5/3 over. So when I move my 5/3 over, what would I have to multiply it by? 3/5. So I get y equals 3/5 f of negative x. And then I can do the replacement of my x plus 2. So y equals 3/5 f of negative x plus 2. And I could leave it like that. I wouldn't have to multiply that negative in through it. Okay? We'll do class example number 4. That's when we'll finish. A function which is g of x, which is x cubed, is transformed into a new function p of x. To form this new function, we stretch it vertically about the x-axis by a factor of 0.25. Reflect it in the y-axis and translate it 3 units to the right. Write the equation of this new function. Okay? So, I stretch it vertically by a factor of 0.25. What's my replacement?
Y was 4y.
Good. Because this factor of 0.25 was a factor of 1/4. Reflected in the y-axis, what's my replacement?
X with negative x.
And translate 3 to the right.
X minus 3.
So when I go in step by step, instead of y equals x cubed, because I can put y instead of g of x, I get 4y equals x cubed. And I can actually do my replacement of my negative at the same time. So I get negative x cubed. What is negative x cubed? Negative x cubed. Move the 4 over, and what would I have? What would I have? 1/4. With the negative, negative 1/4 x cubed. And then I put in the x minus 3. So I have negative 1/4 x minus 3 cubed. So this negative, when I'm looking at the equation, could make it look like it's a vertical reflection as well. And that's because the shape of that x cubed graph lends itself to it could be a vertical or it could be a horizontal reflection. So if I had given you this equation and I said, what are the transformations? And you had said it was a reflection in the x-axis, you would be given marks for this. If you said it was a reflection in the y-axis, you would still be given marks because both would be correct. Okay? So the questions that I have that connect to this part of the lesson are 1B and C, 2B and C, and 4B, C, and D. Question number 5. Given the graph of y equals f of x, if we sketch the graph of the transformed function y equals f of 1/2 x plus 3 minus 8. Take a look at this, the way that this is written, and take a look at how it's supposed to be presented, and what do you notice about the two equations? If you look at the general form, what is the coefficient in front of x? Is it a b times x, or is it just x by itself? It's just x by itself. So what I want to do to this equation is I want to rewrite it, and I want to take out that 1/2. I want to remove that coefficient. So that's factoring a 1/2 out of each of these terms. So then I'm left with a 1x. When I take 3 and I divide it by 1/2, I will get 6. It is important when you're looking at these equations, if there's a coefficient in front of the x, you need to remove that out. Because now when we look at this in terms of what those numbers mean, what does the 1/2 tell us? So what was the replacement? How did I get that 1/2? What did I replace?
X with 1/2.
And what does that tell me to do?
The horizontal stretch by 2.
Okay, so horizontal stretch factor 2. What's my replacement to get this plus 6?
X with an x plus 6.
And that tells me to do what?
Horizontal translation, 6 units left.
Okay. And where does that minus 8 come in? Y with a y plus 8. And that tells me to do what? 8 down. If you did not remove the 1/2 from being that coefficient, what mistake would you have made?
Probably would have said x is replaced with x plus 3.
You would have ended up translating 3 units to the left, not 6 units. So that's the importance, because you'll get the wrong graph when you go to sketch it. So when you go to sketch this, start off by doing the stretch first. Horizontal stretch by a factor of 2. So all of your x coordinates, we're going to stretch. -3 goes to -6. -2 goes to -4. 0 will stay. 3 to 6, and 4 to 8. So then if I was to join these points with a straight line, there's my, so I'll do that one in a different color. Green. Green. Yep. Chosen 2 different shades of green. So there's my stretched graph. Now I can take this graph and move those points that I identified before, 6 units to the left and 8 units down. So this point here, I'm not going to really be able to move because it's outside my graph, so I'm going to start with this one. 6 units to the left and 8 units down. This point, 6 units to the left and 8 units down. This point here, 6 units to the left, 8 units down. And then 6 units to the left and 8 units down. And then join those points together. And I could show this part as extending because it did extend downwards. Okay, so class example 5 and 6. It's about that idea that the coefficient on x should always be 1 before I start figuring out replacements and figuring out what the transformation would be. So if we look at class example number 6, the function f of x, which equals the square root of x, has been transformed into the function g of x, which is negative 2 times the square root of 3x minus 12 plus 5. So again, before we figure out our replacements or anything, we need to rewrite this equation so that my coefficient on x is equal to 1. So what do I need to factor out?
3.
A 3. So when I factor out a 3, I will get 3 times x minus 4. So what are all of my replacements in g of x? How did I go from the square root of x to all of this?
Replace x with an x minus 4.
Okay. What else did I replace?
Y with a y minus 5.
Okay.
X with a 3x.
Okay. Did I replace x with a 3x before or after I did the x minus 4? Think order of operations. Which comes first?
Before.
Before. Because I'm multiplying, and the multiplying comes before the adding and subtracting. Okay, what else did I replace?
A y with a 1/2 y. Negative 1/2 y.
Okay, and does that happen before or after the minus 5?
Before.
Before. So, the function f of x has been transformed to the function g of x by stretching horizontally about the x-axis by a factor of what? So where's my horizontal stretch? My replacement of x with a 3x, so what's the factor? 1/3. Stretch vertically about the x-axis by a factor of, so my vertical stretch was this part in here, so it's a factor of 2. And because this is a negative, I have a reflection in which axis? The x-axis. Translate how many units up? And how many units horizontally? 4. Which direction? Good. So the questions that I would like you to complete for this section, because I gave you questions from 1 to 4 yesterday. So I'm going to add question 6A